let's look at sample test 4. All right, problem number 1. A liquid has an index of refraction of 1.84, which is closest to the speed of light through it. So speed of light is the fastest when it's c, but when we have different medium, it won't be the full speed of light. It'll be some reduced speed of light, and so we can have the equation that v is c over n, where c is the 3.0 times 10 to the 8th meters per second, and n is our index of refraction, 1.84. So we get 3 10 to the 8th divided by 1.84. 163 meters times 10 to the 6th meters per second. And so it's like 1.63 times 10 to the 8th. That'd be closest here. It would be D. All right. A ray of light strikes a diamond at an angle of 25 to the normal. All right, so we got something like this. 25. Strikes it. The angle of the ray reflected off the diamond surface, so the reflected just bounces right back off, and we always have that incident equals theta incident equals theta reflected, so we just have 25. All right, a ray of light shines on strikes a diamond again 25 degrees normal. Find the angle of the ray that refracted into the diamond. So now we're talking about the ray that comes in, and since n equals 1 in air, n equals 2.42 in the diamond, so remember bigger n means smaller angle, so this little theta 2 is going to be smaller than our theta 1, if we call this theta 1. So refracted calls for Snell's law, so n1 sine theta 1, n2 sine theta 2, n1 is 1 sine theta 1, or theta 1 is 25, equals n2 2.42 times sine of theta 2. Theta 2 is inverse sine 1 over 2.42 sine 25 degrees. Theta 2 is inverse sine of 1 divided by 2.42 times sine of 25. Looks good. 10.1 degrees. It looks like an A. Okay. As we saw in lab, which color of light has the smallest critical angle for total internal reflection? All right, so we shone the light in there, and we watched as it all the refracted ray went, so it was starting on the inside, the material, and we watched as the refracted ray got bigger and bigger. As it approached 90, we saw that the blue went in first, and then finally the red went in. So the smallest critical angle was when it went in first, so blue went in first, so we would say C. What is the total impedance for a coil with resistance of 5 ohms and inductance of 0.08 henries connected to a 60 hertz system? So total impedance, Z, is Z of the resistor plus Z of the inductor. For a resistor, Z is just R. For an inductor, it's J omega L. Omega is 2 pi F, 2 pi 60, 377. L is here. And so we're going to get R is 5 plus J times 377 times 0.08. 377 times 0.08. 377 times 0.08. 30.16. Well, 5 plus J 30.2, we'll say. Ohms. 5 plus J. We'll go with that one. Which is true at resonance? So at resonance, the inductor and the capacitor's reactance cancel out, so all we have left is resistance. If we had a Z sub C, it would cancel out with a Z sub L. So that one is true. Inductance and capacitance, no. Current is maximum. Yep, so it's B. All right, if we measure the voltage at an outlet in the lab as 110 volts, what variable is this? It's not the peak, it's the RMS. If it was the peak, it would have to be like 160 or something. So if we had peak for 110, that would be trouble. Okay, which is the closest to the frequency of blue light with a wavelength of 460 nanometers? So we have the wave equation, C velocity, or in this case we're assuming we're talking about air, so we'll go C is lambda times F. So we're given lambda, so we want F is C over lambda, 3 times 10 to the 8th meters per second, divided by 460, 10 to the negative 9 meters. We'll get hertz, 1 over seconds. Let's see, 3 times 10 to the 8th divided by 460 times 10 to the negative 9. 652 times 10 to the 12th. All right. Is that terahertz, I think? There we go. It's A. Continuing on. What is true about EM waves? E is perpendicular to M, so it's a little bit weird notation. M, we probably mean B, but yeah, but it is true that E waves and the B waves are perpendicular to each other, or the electric waves are perpendicular to the magnetic waves. They move at the speed of light in a vacuum, yes. So this one is yes. Their speed is perpendicular to the E field. Yeah, we have the E is perpendicular to B, is perpendicular to V, yes. They always occur together, yes. At least the changing fields, the waves, occur together. So I guess we should say waves. But we'll do A, B, C, and D. All of them are good. So it's changing fields cause changing fields, and so we would have to have a wave to have a changing field. So since it's talking about waves, we'll go with D being true also. It's a little questionable. All right, if a capacitor has a reactance of negative J200, what is the closest to the capacitance? So for a capacitor, X of a capacitor is 1 over omega C. The negative J is kind of the coefficient that makes this be a Z. Actually, this should probably be actually Z and not a reactance. So the reactance is the 200 part. And so 60 hertz system, so we have 377 for omega. C is equal to 200. So C is, bring the C over here and the 200 down here, 1 over 377 times 200. .3 microfarads. I'll go with B. Which has a current that lags its voltage? Inductor current lags the voltage. Capacitor current leads the voltage. So, which is true about AC circuits? Ohm's law becomes Viz. Yes. KVL no longer works. No, it still works. KCL still holds. Yes. Average power depends on the angle phi, the voltage angle minus current angle. Yes. Voltages and currents are represented by phasors. Yes. So we've got A, C, D, E. Alrighty. 13. Consider a cell phone emitting signals at a power level of 3 watts, which is the closest to the intensity at the tower, 2,000 somethings, we'll say 2,000 meters away. Alright, so we've got intensity is power per area. Generally, if we're thinking of a point source, cell phone we'll treat it as a point source, so the waves go out as a sphere, so we'll have 4 pi r squared. Take it as the area of a sphere. And so P is 3 watts, 4 pi, and R then is the distance away is the radius of the sphere, so 2,000 meters squared, so 3 divided by 4 times pi times 2,000 squared. 1,000 squared. Alright, so I is 59.7 10 to the negative 9 watts per square meter. 60 times 10 to the negative 9, 60 nanowatts per square meter. We'll go with B. Okay, 14. Consider unpolarized light hitting two polarizing filters. We'll assume they're one at a time. The first polarizes it vertically, and then the second is oriented to polarize 20 degrees to the vertical, which is closest to the intensity passing through both, assuming that we start with 1,000. Alright, so we have 1,000 watts per meter squared hitting the first one, and this one is unpolarized, going every which direction. Alright, and then we got vertical, and so the light coming through ends up being just vertical, but when we go from unpolarized to polarized, we know we go, if we call this I0, this will be I1, will be just half of I0, and so it'll be 500 watts per square meter, going from unpolarized to polarized. And then we got the next one that's going to be at 20 degrees to the vertical, 20 degrees, and so the light is all up, but then it does have a component, you know, if we can draw component wise, there'll be some component in the 20 degrees shifted direction. So we're going to have I2, we'll call it, is going to be I1, whatever was here, coming in. And remember, intensity goes with cosine squared, where it was cosine squared, whereas the E field magnitude itself goes with cosine. And so we will have I2 is 500 cosine squared of 20. 500 times cosine of 20, that whole thing's squared. So I2, 442 watts per square meter. 442 is closest to 400. Alright, consider being given two similar looking materials, one of which is diamond, the other is glass. How could you use your knowledge of refraction to determine which one is the diamond? Alright, so diamonds, N of a diamond, like we have in the previous example, is big, 240 or 2.42, whereas N of glass is about 1.5 or something in that range. And so we could look at light coming in at an angle on both of them. Say it's coming in at 20 degrees or something. The one, if it's in the diamond, you have a very small angle, whereas in the glass we'd have a larger angle. So we could, if we had something like this, we would say N, how do we want to describe it? This one would be the diamond, this one would be the glass, whichever one had the smaller angle. If we wanted to get technical about it, we could do N1 sine theta 1 equals N2 sine theta 2, and then we could measure the angles and see which one. For example, if we had 20 degrees for theta 1, N1 is, say it was air, that would be 1, and we can calculate like we have been doing. So theta 2 should be sine inverse. This is a little different than what we did before. Sine inverse of 1 over 2.42 sine 20 degrees. Sine inverse of 1 divided by 2.42 times sine 20. We'd expect to see 8.12 degrees, whereas if we did the same calculation for anyway, something along here. So it's a theoretical question. So we could shine the same light, the same angle on both materials, on the diamond and the glass, or the unknown ones, and the one with the smaller angle would be the diamond, something like that. For the same incident angle. You could get detailed and calculate it like we did in lab, calculate the index of refraction or based on the angle to see which one had the index of refraction that matched the diamond or something along those lines as well. All right, let's look at number 16. Get into some problems here. So consider an RLC circuit with RMS source voltage of 110 volts. R is 10 ohms, X sub L is 100 ohms, and X sub C is 80 ohms. Assume the phase angle of the voltage source is 0. So we've got our circuit. RL and a C. Got some current. Got source voltage. It's at an angle 0. We've got R. We've got JX sub L. We've got negative JX sub C. We have some voltage VR. VL, VC, so forth. So find the total impedance. Impedances, so these are all three in series, three impedances in series, and so they would just add just like resistors do. So we're going to have Z of the resistor plus Z of the inductor plus Z of the capacitor, which is R plus R plus J X sub L minus JX sub C. And so for this problem, we got 10 plus J100 minus J80 equals 10 plus J20 ohms. In rectangular form, if we want to do polar form, we can say calculate the magnitude of Z total. It's just thinking of it like a vector. One component is, say the X component direction is 10 and the Y component is 20, so it's just going to be the square root of 10 squared plus 20 squared. Alrighty. .4 ohms, and then the angle, we call it phi, the power angle, phase angle, inverse tangent of X total over R, and same kind of, we've got R and X, theta here, magnitude of Z here, or not theta, phi. Alright, so phi is inverse tangent of X total, which is 20, divided by R total, or R, which is 10. Get a number here, 63.4 degrees. So we could also say Z total is 22.4 at an angle 63.4 degrees ohms. Putting the phasor complex number in polar form instead. Either one is good. Find the current provided by the source as a phasor. So we're going to, this means the current should be a complex number. And so remember Ohm's law in AC becomes Viz. So I becomes V over Z. I is the total, so you think of a little circuit here for the source, and Z total. We have the same I as above, right? This is, all these have just been lumped into one. We have the same source. All right, so I is going to be V sub S over Z total, going from the generic Ohm's law into our specific case here. V sub S says the voltage is 110, So that's the magnitude of the, and it said to use 0 for the phase angle, so we'll do that. 110 angle 0 volts, and Z total polar form is easier to do dividing in, so we'll go with that. 63.4 degrees ohms. All right, so when we do complex math, when we have them in polar form, to get the magnitude of the answer of a dividing problem, we just divide the magnitude. So 110 divided by 22.4, get 4.91. Okay, so I is 4.91 in magnitude, and the phase angle, when you divide complex numbers, you subtract their phase angle, top minus bottom. So this is going to be 0 minus 63.4, so it's just going to be negative 63.4 degrees. And current is in amps, since voltage was in volts and current and impedance was in ohms. Okay, current as a phasor. Find the voltage across a resistor as a phasor. So V sub R, again, we've got V equals IZ, Ohm's law still works, but now it's the same current, there's only one current, but we want Z of the resistor, which is just back to our old V equals IR version. But now I is complex number, 4.91, angle negative 63.4 degrees, and R is 10. So V sub R is just, again, this is 10 angle 0 if you want to think of it that way. Basically, you just multiply magnitudes, and so we get 49.1 angle negative 63.4 degrees volts. Voltage across the inductor. So V sub L, again, V equals IZ, but now it's for the inductor. Everything has the same current, so it's the same I we've had before, but Z of the inductor is JX sub L, or J100, and so 4.91 equal negative 63.4 times J100. J100, a J, remember in our phasor diagrams, the real part, imaginary part, is the J component is the vertical part, and so this would be 100 up on this axis. So we can think of it, if we want to do it in polar form, it's 100 angle 90 degrees. So again, multiplying is easier in polar form, so let's put them both in polar form. Alright, so when you multiply complex numbers in polar form, this is volts, this is ohms. I'm sorry, this is amps, this is ohms. Multiply magnitudes, add angles, and so 4.91 times 100 is going to be 491, and the angle is going to be 90 minus 63.4. 26.6. So 491 at an angle of 26.6 degrees. Volts is the L as a phasor. And we've been using the bar on top to think about, to remind ourselves that it's complex. So that gets tiresome, so we don't always remember to do that. Okay, voltage across the capacitor. Same story, V sub C, I Z sub C, 4.91. Angle negative 63.4, same current and everything. Z of the capacitor is negative J80. Again, let's put it in polar form. So 4.91, angle negative 63.4. And negative J80 is 80 at an angle of negative 90 degrees. Ohms. And so multiply magnitudes, so V sub C, magnitude-wise, 4.91 times 80, 393 volts. And the phase angle is those two combined, added together, so negative 153.4 degrees volts. All right, that was Viz one more time. Draw a phasor diagram showing the 4 voltages and the current. So we get our axes here. We've got a real We got our imaginary, where the J components are. And we said our voltage source, V sub S, was at 0. We've got our I is negative 63.4, so if this is 45, I don't know, something like this for I. Okay, this is 63.4. And then V sub R is also at negative 63.4. That's what it's supposed to be. V sub R, voltage across a resistor, is always the same as in same phase angle as the current through the resistor. V sub R is 49 compared to this being 110, so just getting somewhat a little more accurate. That one would be V sub R, be shorter than V sub S. Okay, in line with I. Inductor, for inductor, the current lags behind the voltage. So, and if we look at the inductor's voltage, is 26.6, so we need 26.6 here. But compared to the current, we got a 90 degrees, and V sub R is big. It's probably not really to scale, but V sub L. So V sub L is up here. Current's lagging 90 degrees behind V sub L, so that's good. And then finally V sub C, voltage of the capacitor, these are all going through 0, is also going to be big. Not quite as big as that one. Something like this maybe. Be V sub C, and it's 90 degrees behind because capacitor current leads the voltage by 90 degrees. And we think of omega is here, so when we're thinking about leading and lagging, think of a person standing here. Voltage V sub L comes past first, then the current comes past 90 degrees later, and then capacitor comes past, capacitor voltage comes past after that, 90 degrees behind the current, which is leading the voltage for the capacitor. Okay, so there we go. Right equation for the current is a function of time. So I, as a function of time, is going to be I RMS square root of 2 to get the peak value, sine omega t plus whatever the current phase angle is. Alright, so IRMS was 4.91 amps times the square root of 2 sine. Didn't give a frequency, we'll assume 60 hertz. So omega is 377 radians per second. Alright, so we got 377 T plus the phase angle of the current is negative minus 63.4 degrees. We can multiply it out, I guess. 4.91 times square root of 2, 6.94 sine 377 T minus 63.4 degrees. That is amps, and that is I as a function of time. Sine wave. Okay, write an equation for the inductor voltage as a function of time. Same process. V sub L of T is V L RMS square root of 2 sine omega T plus whatever its phase angle is, theta of V sub L. Alright, so VRMS for the inductor is 491. So 491 times square root of 2 is going to be, yes, 694. So V sub L is a function of T, 694 sine 377 T plus, yes, plus 26.6 degrees volts. Okay. What is the average power produced by the source? Alright, so the source is feeding all the other things. It's the active device. All the other ones are passive device absorbing the power. So we could just say what is the power absorbed by the load just as well, calculate that. But so let's do this a couple different ways. But we can say P average is, in general, IRMS, VRMS, cosine phi, the power angle. All right, which phi is angle of the voltage that we're talking about minus angle of the current we're talking about. In this case, we already have calculated phi, and we have, so this would be for the source, which is the only current we have, and again, the source voltage and the phase angle of the total load, for example, or the angle between the source voltage and current. In this case, we had the 4.91 was IRMS, VRMS for the source is 110 volts, amps. Cosine phi was 63.4 degrees. $242 watts. Since our circuit, we know that capacitors and inductors don't consume any real power or any average power. They have energy, they're passing it back and forth, but on average the average power is zero. On average their power is zero. So the resistor is the only component that's taking real power or average power. And so we could also just calculate the power in the resistor would be what the power is, the only power that the source has to provide. So we could also say P sub R is magnitude of I squared R, RMS. And so the 4.91 squared times the resistance was 10 in this case, and that also comes out 242 watts. Okay? So we could do it either way, with a little bit of an argument there that P source and PR are equal. What is the average power absorbed by the capacitor? P of the capacitor is equal to 0, so would P of the inductor be 0 if I asked that one? All right, they don't consume any average power. It's just oscillating back and forth. Their power is just oscillating back and forth. What is the power angle? We've already done that before. The power angle is the impedance angle, 63.4 degrees. Okay. Number 17. Consider another RLC series circuit. Source voltage given as a function of time here. We've got R and C. Find the reactance of the capacitor. So X of a capacitor, 1 over omega C. We've got omega is whatever's multiplying T in the cosine. So that's 1 over 377. And then C is 120 micro. One divided by 377 times 120 times 10 to the negative 6. 22.1 ohms is X of C. Ask for the reactance, okay? If we wanted Z of the capacitor, it would be negative J 292.1 ohms. Okay, draw the circuit. It says it's a series RLC circuit. It hasn't told us anything about the inductor yet. But just the same circuit we had before. Some VR, some VL, some VC, some current, source, some R, some ZL, some ZC. Okay. Find the inductance needed to put the circuit at resonance. So at resonance says that X of the inductor equals X of the capacitor. Reactance of the inductor and capacitor are equal at resonance. And so omega L, this X of L is omega L, X of C is 1 over omega C. And so we've got X of, which we've already calculated, X of C is 22.1, and we've got omega, bring this over here, omega is 377 times L, so L is 22.1 ohms over 377 radians per second. 22.1 divided by 377. 58.6 millihenries would give resonance, okay, for this circuit. Find the total impedance at resonance. Also, Z total is R plus JX of L minus JX of C. We just set these two equal to each other, so Z total, so they cancel each other out. So Z total is just R. So Z total is R is 25 ohms. Okay. Find the total current in RMS as a phasor. In RMS as a, anyway, find the current. Current, remember we're going to do Ohm's law in AC, Viz, so I is V over Z. Again, I is the only current in the circuit. V, we want the total voltage across everything, so that would be the source voltage. And Z then is the total impedance. In this case, to get the source as a source voltage as a phasor, this is, remember, whatever's multiplying the cosine is the peak. When we draw a sine wave, you know, the coefficient, I did it in cosine, usually it would be sine. Okay. Anyway, if we start with cosine, just make everything cosine and it all works out the same as if we had done it with sines. So anyway, the peak value is 170 here. We want RMS, so VRMS is V peak over square root of 2. So 170 over square root of 2. $120.2. That's the magnitude of VRMS, 120.2 volts. So we'll use that for our V sub S here, and we'll just, I think it is given, there's no phase angle there, it's just cosine omega t. And so the phase angle is 0 degrees for the voltage. And yeah, let's just go with it. And then the total Z was just R, which was 25. .81 amps is the magnitude of I. What's the phase angle? Well, what's the phase angle of resistors? 0. All the angles are 0. 0 minus 0, 0. All right, so the current has a 0 phase angle when we're at resonance, or it has the same angle as the voltage. So if the voltage is at 0, current's at 0. Find the inductor voltage magnitude at resonance. So V sub L, again, whichever condition it is, V equals IZ. And so this is our only source current, and we want Z of the inductor, since that's what we're talking about now, voltage of the inductor. And so that's going to be our 4.81, angle 0 degrees, times ZL, which was J22.1, I think. Right, capacitor was positive was negative J22.1, so the inductor has to have opposite, anyway, same magnitude but opposite sign, so it's plus J22.1 for its Z, or 4.81 angle 0 degrees times 22.1 angle 90 degrees. Remember, a J is a 90 degrees. And so 4.81 times 22.1, 106.3 angle 90 degrees volts for VL. Alright, so this makes sense because the inductor, the current is supposed to lag behind the voltage by 90 degrees, so the voltage better be 90 degrees ahead of where the current is. So that is good. Okay. Number 18. Consider a 4.5 gigahertz EM wave with a peak electric field magnitude of 400 or 100 volts per meter, so E naught is 100 volts per meter. What is the peak magnitude of the magnetic field? So we've got E over B equals C, or we can rearrange. So B is E over C. So it's 100 volts per meter over 3 times 10 to the 8th meters per second. .3 times 10 to the negative 9 Tesla would be our B naught, the peak B. I should be checking my answers to see if I agree with myself. Alright, calculator shows I did it wrong. It's 10 over, I got a 10 and not 100. Let's do 100 divided by 3 times 10 to the 8th. Yeah, okay, we need another 3 there. 333 times 10 to the negative 9 Teslas. What is the speed of this wave in the air? Well, in air we'll assume that the index of refraction is just 1, and so V is equal to C for EM waves in air, whichever one it is. So V is equal to C. I guess we can give a number 3.0 times 10 to the 8th meters per second. What is the wavelength of this wave? Wave equation, C is equal to lambda F, and so lambda equals C over F. 3 times 10 to the 8th meters per second divided by F, which is 4.5 giga. We got kilo, mega, giga. Mega is 6, giga is 9. 10 to the 9th hertz. A hertz is 1 over seconds, so that cancel with the 1 over seconds over there. They're going to get meters. That's good. 3 times 10 to the 8th divided by 4.5 times 10 to the 9th. Okay, 66.7 times 10 to the negative 3 meters, 66.7 millimeters equals lambda. Okay. What is the total energy density? Total energy density is, so the magnetic part and the electric part both have energy densities that are equal to each other, so we can just basically take it times 2, or take the electric times 2, so the electric energy density is 1/2 epsilon naught E, and so we can just do epsilon naught E, I'm sorry, 1/2 epsilon naught E squared. Epsilon naught E squared. Let me double check that equation. Now I'm doubting myself. Let's see. Alrighty. Yes, squared. Okay. Epsilon naught is 8.854 times 10 to the 12, negative 12, and E 100 volts per meter squared. All right, 8.854 e negative 12 times 100 squared, 100 88.5 10 to the negative 9 joules per cubic meter. So it's a volume type of density, 88.5. Okay. 88.5 nanojoules, or 10 to the negative 9 joules per cubic meter. If the wave emanates from a point source, has a power of 500 watts at the source, what is the intensity 400 meters away? So kind of ignoring that, giving new numbers, we want the intensity is power over area, the area of a sphere, and so it's power over 4 pi r squared, surface area of a sphere, and so it's 500 watts divided by 4 pi 400 meters squared. So the intensity is 249 times 10 to the negative 6 watts per square meter intensity. Okay, looks good. Last page. A little bit messy there. Okay, so got a ray of light incident on thick glass container with water inside, 40 degrees as shown. Find the angle of refracted ray as light enters the glass from the air. The refracted ray is a ray. Oh, my pencil. I thought I had a new sharp pencil, but it's got a broken lead. We'll go back to the dull pencil. So this angle here is what we're talking about, refracted ray in the glass is theta 2. Mark it as theta 2 in the diagram and find what it is. Okay, so Snell's law, let's call this one N1 in air is 1, N2 in the glass, N3 in the water. All right, so this is theta 2, this is theta 1 is the 40 degrees. All right, so N1 sine theta 1 equals N2 sine theta 2. In this case, N1 is 1 sine of theta 1, which is 40 degrees, equals N2, which is 1.5 sine theta 2, which is what we're looking for. So theta 2, solving for theta 2, divide through by the 1.5 and take inverse sine. 1 over 1.5 sine 40 degrees. Don't do that. Inverse sine of 1 divided by 1.5. That fraction times sine of 40. 25.4 degrees is theta 2. Okay. Determine the angle of refracted ray as the light enters the water from the glass. Mark this as theta 3. So theta 3 is the angle here in the water. 3, theta 3. Just knowing these two perpendiculars are parallel to each other, and so the alternate interior angles are equal. So this one is also theta 2 in here. So that's the incident angle on this new interface we're interested in. So we're going to have the same kind of thing with Snell's law. N2 sine theta 2 equals N3 sine theta 3. N2, 1.5 sine theta 2, which is 25.4, equals n3, 1.33, sine of theta 3. Theta 3 must be inverse sine of, divide through by 1.33, 1.50 over 1.33, sine 25.4 degrees. Inverse sine of 1.5 divided by 1.33 times sine 25.4. 28.9 degrees is theta 3. Okay, determine the critical angle for the glass to water boundary. Right here, glass to water boundary for total internal reflection inside the glass. So we're going to have light coming in from the glass, hitting this boundary, and we want to know when it all stays in and none of it refracts into the water. Right, does not exist if total internal refraction is not possible for this interface. So we have theta critical is inverse sine of n, I guess we'll call it n2 over n1 in general. Okay, where 1 is where the light ray starts, 2 is where it ends up. So in this case, theta critical inverse sine is inverse sine of, it ends up in the water, so it's going to be 1.33. Right, in this case, this is going to be n water, and n1 is going to be n glass. All right, so 1.33 over 1.50. So theta critical. We know it's going to work because inverse, the top number is smaller than the bottom, so it will exist. So let's go ahead and get our inverse sine of 1.33 divided by 1.5. 62.5 degrees is theta critical for glass to water. All right, part D, do the same thing, but now from glass to air. So we're going to think about what light coming over here, bouncing off this interface, and what is the critical angle to keep it, all of it reflecting inside the glass and none of it going out into the air. So same kind of thing, theta critical is inverse sine. Again, it's going into air now, so we put n air on top and n glass, where the reflections are happening on the bottom. So inverse sine of n for air is 1, n for glass is 1.50. So this theta critical for glass to air is inverse sine 1 divided by 1.5. Again, we know it's good because the top of the fraction is smaller than the bottom. 41.8 degrees. All right, so it doesn't have to have a sharpened angle going towards the air to get it all to stay in as it does to the water, because the water has a larger index of refraction. Okay, part E. Find the reflected angle for the light entering the glass from the air. Sketch a reflected ray on the picture. All right, so we're going way back to the beginning. The ray coming from the air hitting the glass. If we want to look at the reflected part that doesn't go in, remember we have the law of reflection that the incident is equal to the reflected. I guess I'll call it theta r. So theta r is equal to theta I is equal to 40 degrees. Reflected. Reflected and refracted are both r, but we're talking reflected here. Alrighty. And that's the test.